So here are some examples to help us understand the role of work done by non-conservative forces in our conservation of energy equation. So read through this problem. There's no non-conservative forces doing work in this first problem. So read through it, press pause, and try to work through it on your own, and then press play when you want to go through it with me. So this child is going to be swinging back and forth. If I think of all the forces acting on the child, there's going to be gravity pulling straight down. And then you can either say, there's like the normal force of the seat pushing up on the child, or you can say there's tension on the swing pulling up like that. That force is a centripetal force. It's always going to be pulling perpendicular to the direction the object is moving, so that force is not doing any work. So the only force that's doing work in this case is a conservative force. It's the force of gravity. And because the only force that's doing work is a conservative force, mechanical energy will be conserved. So we can use our simple formula Ki plus Ui equals Kf plus Uf. So here's our general formula. This term in this case is 0. There are no non-conservative forces doing work. There are non-conservative forces acting on our object, whether you call it the normal force of the swing on his butt or, the tension in the rope on the whole thing. That is a force, and it is a non-conservative force, but it's not doing any work because that force is acting perpendicular to the direction the object is moving. So this term here is going to be 0, and our equation simplifies to just Ki plus Ui equals Kf plus Uf. So I'm going to choose the maximum height as my initial because that's something I know. And I'm going to choose when he's at the lowest point as my final because that's what I'm being asked about. So there's my work done by non-conservative forces is 0. And so I can use Ki plus Ui equals Kf plus Uf. Initially, when we're at that maximum height, the speed is 0, so the kinetic energy is 0. And then when I'm at the lowest height, if I put my y equals 0 at whatever position the kid is at the lowest height, I can say the potential energy there is 0. And then I just make sure that the y value here is how high I am above this height here, which is exactly, what they define, 3 meters above the lowest point. So my y equals 0 will be at the lowest point, and my y initial will be 3 meters. The m cancels, and here I've plugged in for y initial, and then I can solve for v final. Okay, so that's my very simple use of the conservation of energy equation. Let's make it a little more complicated. So the same initial things, except initially the child reaches that maximum height of 3 meters above the lowest point. Then you're going to give the child a push with a force of 250 newtons in the direction the child is moving, and while you're pushing, the child moves 10 centimeters. Okay, so now we want to know what's the maximum height. So if you think about what's happening here, I hope you agree that the child is going to go higher after you give him this little push. And in terms of conservation of energy, what we can understand is that when you push the child in the direction the child is moving, you do positive work. You push something and it moved in the direction you pushed. That means that you've done positive work on the system. If you've done positive work on the system, you're putting energy into the system, and that's going to increase the total mechanical energy. So now when the child swings up, he's going to reach a higher height. Okay? So again, I'm going to be using this expression. This is the expression that we're going to use for most of this chapter. And now there are non-conservative forces doing work because you pushing, that is a non-conservative force, and your pushing force does work. The tension still is not doing any work because that's perpendicular to the direction of motion, but your force is doing work. So we are going to need to calculate how much work your force does, that non-conservative force. Well, because we're looking in one dimension and it's a constant force, we can use the very simple formula that the work is equal to F times D, where F is the magnitude of the force, D is the distance the object moves while the force is pushing on it. That's going to be 10 centimeters. I need to do that in meters. So we find that when you give that push, you do 25 joules of work. And that 25 joules of work is going to be added to the total mechanical energy of the system. Now when I'm choosing my events, I want my initial event to be before the push and my final event to be after the push. But also, they're asking me what's the maximum height now, like after the push. So I'm going to choose my initial event will be when I reach the maximum height, but the time that I reach the maximum height before the push. And then I'm going to get the push, and then my final event is going to be when I reach my maximum height again after the push. So both of my events are when I'm at a maximum height. So K initial is going to be 0, because when I'm at that maximum height, I'm not moving. And then my final is also when I'm at the maximum height, but after the push. So K final is also going to be 0. Okay, so both K initial and K final are 0. And then when I'm at that maximum height, my U initial, that's the maximum height I have before the push, which is 3 meters. They told me that in the problem. And the final Y final that I'm looking for is the maximum height I have after the push. That's what I'm asked for. That's what I'm going to solve for. Here my mass does not cancel. And your mass only cancels if the work done by non-conservative forces is 0, because you have an M in each of these expressions. Once you start involving the work done by non-conservative forces, your mass will not cancel anymore, and the mass does matter. So I've included all the values here, and I'm including the 25 joules of work that you did when you push on the kid. And then I can solve for Y final, and as you expect, it's bigger. Initially, the kid only got up to 3 meters above the swing, or above his lowest point, and after the push, now he reaches a height of 3.13 meters. Let's just do one more problem to help us see what's happening here. And in this case, everything is the same, except now you're going to push on the kid in the opposite direction. So while the kid is swinging towards you, you exert a force on him. And I hope that you can see that when you do that, you are going to be doing negative work. You're pushing to the left while the kid is moving to the right. You are doing negative work. And as a result of the negative work that you've done, the kid is not going to swing up as high because you are taking energy out of the system. Okay, so now this value here is going to be negative. So my total mechanical energy is going to be smaller than it was before. So now when I calculate how much work any non-conservative forces did, I'm just going to, the only force that's non-conservative that's doing work is your pushing force, but now you're doing negative work. And I put that in there, the negative sign, because I know that you're pushing in the opposite direction the object is moving. So now you're doing negative 25 joules of work. I'm still going to use this expression. My events are still going to be when I'm at the maximum height before the push, and my final event will be when you reach a maximum height after the push. So it will still be the case that Ki and Kf both equal 0. But now my work done by the non-conservative forces is negative. That's taking energy out of the system, and so you reach a smaller height than you had before.